Good afternoon, dear colleagues. Many thanks for the organizing committee for getting us together at these difficult times for this nice conference to have some joint discussions. And many thanks for kind introduction for the session chairman, Mr. Chairman. I represent a team of researchers from Kuban State University, Krasnodar, Russia. We are supervised by Professor Evgeny and Professor Natalia, and we are working together with Mr. Ilia from our team. So the short outline is, first of all, I will give some motivation, then briefly describe the analytical model which we are employing for time reversal imaging, and provide some examples of applications to metallic and composite structures, and finally some conclusions, outlook, and acknowledgements. So the motivation is that one of the main and challenging problems of guided wave-based structural health monitoring is not only damage detection, but also damage imaging, which means the estimation of damage size and severity. And to do this, we should keep in mind that in SHM applications, we have a distributed network of actuators and sensors, and actually that's the only information which we have about the structure, these signals from these sensors or actuators. And we need to use this information just to obtain the location of damage and also its shape and extent. And to do this, there are a great variety of approaches for imaging, but among them, one of the prominent is so-called time reversal method. It was proposed by Matthias Fink in early 1990s. And the idea is that we have a set of receivers or transducers which are capable to catch signals emitted by the source and reflected or scattered by the obstacle. And we could do some re-emission of these signals. And finally, due to the physical properties of the media, these re-emitted signals should definitely be concentrated or get together at the point where the initial source took place. So they were proposed two concepts like time reversal cavity and time reversal mirror. And these were initially for acoustics, but further on, these findings were generalized for elastic structures. And in this case, it was proposed not to perform such re-emission in physical plane, but in computational domain. That's an example of the paper of Wang and Rose and Fuku Cheng from 2004. The idea is that we have an actuator and we have some sensors. We get information from the sensor, and after that we do this re-emission in virtual domain, so using some computational approaches. For example, the authors, they have implemented plate theories, and finally we can have some map where from this map we can judge about the place where our damage is taking place. Our idea is to provide this transfer, and the most important part here is that to do this re-emission, we need a structure transfer function. This could be done in various methodologies using plate theories, finite elements, but for our team it is typical to do this in a analytical way. Very briefly about this approach, we are assuming that we have an infinite elastic laminate or infinite elastic plate. We simulate each layer separately as a with a generalized Lamé equation for time harmonic motion. So we can assume that our plate could be either isotropic or anisotropic. We simulate each layer. We're assuming that we have stress and displacement continuity between sublayer boundaries. We assume that our plate is stress-free except the area where some loading is applied. So the initial is that we have the starting point is that we have some measurement points, measurement locations at which we managed to obtain some signals regarding our plate and some signals with the plate with damage. And we are starting some re-emission, some simulation of re-emission from these sensor locations. And this re-emission is simulated with this analytical approach. And to do this, we need somehow to simulate the excitation. This is provided by the vector function q. And within this analytical approach, displacements generated by such surface load, they are sought as a convolution of the green function of the structure with these unknown surface tractions. And due to the infinite elongation of the plate along horizontal coordinates, we can employ Fourier transform technique and to obtain at first such twofold integral. And after some manipulations, some asymptotic expansions using residual theory, we can finally obtain an expansion of this integral as a guided wave expansion, which allows on one side relatively fast computations for the evaluating re-emitted field, while on the other hand it allows manipulating certain normal modes, certain Lamb waves or quasi-Lamb waves if we are talking about laminate composite structures. And for such derivations, we need some, of course, input data, and we currently are investigating two types of these. First of all, we are studying distributed sensor networks, which are piezoelectric buffer active sensors. And to gather information from these, we are using a conventional digital oscilloscope connected with USB with our laptops or something like this. However, we also developed a custom multi-channel system which allows switching between different piezoactuators and allows one-by-one excitation of piezoactuators in the network. And nevertheless, we get some voltage from the piezos. After that, we apply Fourier transform from time domain to a frequency domain and obtain the spectra. And this spectra, which we get from our sensors, is serving as an input for our computational model. Of course, since we want to do some time reversal technique, we need to have the complex conjugate of our spectrum. And with this respect, if we are having a piezoelectric sensor network as an input to simulate it, we are investigating pin force models so that the impact of the sensor on the plate or its influence on the plate is simulated as pin forces distributed over its border. Another model is if we are using a scanning laser vibrometer for obtaining the data for further emission. This is the joint work with Helmholtz University Hamburg with Professor Rolf Lammering. In this case, we are obtaining out-of-plane velocities at certain points on the surface plate. Again, do some Fourier transform to frequency domain, and here the history is almost the same, but in contrast to the previous derivation, here we have vertical point load. This is mainly because the idea is that since with the vibrometer we are measuring out-of-plane velocities, as a load for simulating remission from these sensing points, it's quite natural to use vertical surface loads with the amplitudes equal to the signals obtained from these points. And in this case, if we are considering a laser vibrometer, due to the peculiarities of this technique in the frequency range of interest, let me say up to 400 kilohertz, we're mainly sensing A0 mode, and therefore in the derivations from here, we are preserving only the term relating to this mode. So we have some save of computations. So the next step is to estimate feature location, which under the feature we mean here damage. So we assume that we have a certain amount of transducers marked with yellow and certain amount of sensors marked with green. And with this respect, we have some test function. And further on, we have two cases. If we consider distributed sensor network, in this case, each term in this sum is sought as a root mean square of the signal of the emitted signals. And due to the fact that root mean square can be converted to frequency domain, we have a lot of savings in computational costs. And in this case, this term in this sum is obtained within this formula. If we have laser vibrometer measurements, another approach is implemented. It provides better results. In this case, we obtain maximum value from all the remission points over all the times. And in this case, we have also have a sum of signals emitted from sensor points. Again, I should emphasize that in this case, N A and N they could be either equal or not with respect to the technique employed. And after that, what we need to, of course, we should evaluate this test function at a certain domain, at a certain computational domain. After that, we do some normalization of the data, and as the feature center, we select a point x at which this maximum is achieved. And afterwards, to obtain the feature extent, we need to do some thresholding of this function. And the support of this function after this thresholding is called the feature extent. This idea was proposed first in the paper of Fink and co-authors in 2002. And so we considered several test cases, and the first case that was an aluminum plate equipped with 8 piezo sensors located 200 millimeters one from the other. The plate was 1 meter to 50 centimeters and 2 millimeter thick. And this is just an example. If we can see the signal from piezo A to piezo B with the obstacle located at this position, and the obstacle was 10 millimeter cylinder clamped to the plate with the additional mass of 100 gram, and we used water as a couplement. And in this case, one can see that there is certain difference in the signals, damaged or baseline. And I should also emphasize that as an input for remission, in this case, if we want to obtain damage, we need to use this difference between damaged and baseline signals. And this is the difference. One can see that its amplitude is sufficiently smaller than of the original signal. Let me say it was 15 millivolts, while here it's less than 1 millivolt. And the same thing we can see with the spectrum. Well, this is the spectrum of the baseline signal. This is the spectrum of the difference. And one can see that we have almost no meaningful values after, let me say, about 100 kilohertz. And what we've tested first is the influence of the excitation signal. We've considered 2 types of the signals. The first one was very popular narrow band, let me say, 5 cycle sine function with Hanna window. And in this case, one can see that we have some strong local maxima here. But if we take a look from above on this imaging function delta, which was introduced earlier, sorry, we have a lot of additional points, local maxima, so that our global maxima is, let me say, not very easy to find here. But if we use broadband 2 microsecond excitation, and here are the signals, excitation signals, and here are their spectrums. In this case, surprisingly, we have very nice image of our obstacle, which was in this case a cylinder of diameter 10 millimeter located at this point. And we can very nicely resolve this damage. That's actually the only local maxima. And what should be also noted that we had our test area, our computational area, far away from the sensor network. So nevertheless, we have only one local maxima here. So these emitted signals, they strongly converge at this point. This is mainly the reason is that when using this broadband signal, we enjoy these low frequency signals, which we see here. So we can take them into account, and they provide us this nice only local maximum. And we've done some tests regarding the how we can resolve the location of our damage and its extent if we use such technique. So we had 3 test locations marked here. This is location 1, location 2, and location 3, and 3 test sizes of our damage cylinders of 8, 10, and 12 millimeters. And in all the cases, we had a very nice coincidence between real location of the damage on the plate and estimated location. So the discrepancy was, let me say, less than 5% for each testing case. Afterwards, we decided to compare either we can resolve the damage size with such computations. And here there are cuts of these surfaces along X and Y axis. And we can see that if we put them together at one on certain plot, we clearly see that if we have bigger damage, so let me say damage of 12 millimeter in diameter, it definitely provides wider wider area at these plots. So when comparing, for example, here green curve, which is for 12 millimeters, and red curve for 8 millimeter, we can see that definitely this is thicker or wider area here. And the same situation is observed for almost all the locations. However, it should be noted that judging between 8 and 10 millimeters is quite an issue. For example, here or here, you can see that these curves are almost the same. Another case study which we've carried out was the case of two obstacles. So we've taken two cylinders of 15 and 10 millimeters, and while the first study they were put together pretty distant, one from the other at about 140 millimeters, and we can clearly see two local maxima, just two maxima, and they were in a nice coincidence with real location of the damage. And in the second test study, we put them quite close one to the other, so the distance was just 20 millimeters, and nevertheless we managed to resolve these two damage positions, disregard of the pretty sparse sensor network. And afterwards, we've done also some studies for carbon fiber reinforced plastics that were done in parallel, and the case study was done for cross-ply laminate, and in this case we have just 4 piezoelectric actuators and about 32 sensing points, and in this case sensing has been done with the laser vibrometer. And again, we have pretty strong loss of amplitude if we consider pristine and or baseline and damaged scenario. So this is input for the model is pretty low amplitude, and this amplitude could be even very, very tiny amplitude. Nevertheless, disregard of such tiny amplitude of the input signal, we can nicely reconstruct the location as well as the size of damage, but in contrast to the case of aluminium, we had to use sufficiently more re-emission points to achieve the same resolution. So in case of carbon reinforced plastics, with 8 re-emission points, we were able just to recover the location of the damage rather than its extent. And if we have, let me say, 16 points, in this case, we can judge about the damage size, but nevertheless, in contrast to isotropic case, we have quite strong mismatch in size. But that's mainly due to the fact that for carbon fiber reinforced plastics, high frequency components of Lamb waves are strongly damped out due to the viscosity, and that's then therefore it would be quite an issue to resolve small scale damage, at least with A0 mode. So there were two case studies for 2 case locations, somewhere at the middle of the test domain and somewhere closer to its border, but nevertheless in all 2 cases we managed to resolve 2 damages and several damage scenarios, and managed to obtain more or less to judge about the type of damage or size of damage which was installed in the structure. So some conclusions: we've developed a computational analytically based time reversal approach for damage localization and approximate estimation of its size in isotropic and anisotropic waveguides. And the results presented above for aluminium and carbon reinforced plates, at least for the samples which we've considered, they confirm the possibility of smart localization of the homogeneity, as well as gives us some optimism in estimating its size. As the future work, we are intending to implement the developed approach for carbon reinforced plastic samples with distributed network, and also to investigate the tolerance of the proposed technique to changes in environmental conditions, for example, humidity, temperature, etc. And many thanks for your attention.